So today's lecture is on section 2.2 from your textbook entitled Separable Equations. So the first type of differential equation where we're really going to learn a technique for solving is called a separable differential equation. So we're going to start off by focusing on a special type of differential equation to begin with, and that's a first order differential equation that can be put into the form dy dx equals f of xy, where f is a function that could depend both on the independent variable x and the dependent variable y. Right out of the gate, we don't necessarily know that a first-order differential equation can automatically be put into this form. Not every first-order differential equation can be, but we're going to say, suppose that we have a first-order differential equation that can be written in this form, and then we're going to further suppose that the function f of xy on the right-hand side of the equation can actually be separated into a function that depends just on the independent variable x and a function that depends just on the dependent variable y. So it can be written as the product g of x times h of y. So when you can write your differential equation in this form, dy dx equals g of x times h of y, you have what's called a separable differential equation. So that exactly is the definition of a separable differential equation. A differential equation is separable provided it can be written in the form dy dx equals g of x times h of y. So let's take a look at a couple of examples recognizing whether a differential equation is separable or not, and then we'll learn the method for solving such equations. The first example we want to look at is, suppose we have the differential equation dy dx equals x squared y plus x squared. And so we would say, is this a separable differential equation or not? And the question we want to ask ourselves is, can the function on the right-hand side, the x squared y plus x squared, can that be separated into a product of a function just depending on x and a function just depending on y? In this case, we see that the answer is yes, because if we factor an x squared out of the function on the right-hand side, we can rewrite the differential equation as dy dx equals x squared times y plus 1. So we see that the x squared function could be considered the g of x, and the y plus 1 function could be considered the h of y. For our second example, let's look at the differential equation dy dx equals x times e to the x plus y. And again, we want to ask ourselves the same question. Is this differential equation separable or not? Can the function on the right-hand side be separated as a product of a function just depending on x and a function just depending on y? And at first glance, this differential equation might not appear to be separable, but we remember our rules of exponents, and we see that the term e to the x plus y can actually be written as a product e to the x times e to the y. So the function on the right-hand side actually simplifies as x e to the x times e to the y. So the x e to the x is playing the role of the function g of x, and the function e to the y is playing the role of the h of y. So again, this second differential equation is also separable. As a third example, suppose we have the differential equation dy dx equals x plus y. And again, we want to ask ourselves the same question. Can the function on the right-hand side, the x plus y, be separated as a product of a function just depending on x and a function just depending on y? And you look at this for a while and you think about it, and you can convince yourself that it's just not possible to write the function x plus y as a product of a function just of x times a function just of y. That's maybe not so easy to see all the time. You kind of need to convince yourself that it's not possible, but it's not always so easy to, prove it. But we can look at this differential equation and we can see that it's not separable. Okay, so now we have a good picture of recognizing whether a differential equation is separable or not. So now the question is, okay, how do I solve a differential equation once I recognize that it's separable? What's the technique? So suppose you start off with a separable differential equation, and you've already separated the variables on the right-hand side. So you've written it as dy dx equals g of x times h of y. Well, now you're going to do a little bit of algebraic manipulation. You're going to treat the derivative on the left-hand side as a ratio of the differential dy over the differential dx, and so you can actually rearrange the differential equation with that in mind and separate the dy and the y's on one side of the equation and the dx and the x's on the other side of the equation. Rewriting the equation in the form dy over h of y equals g of x dx. then you integrate both sides of the differential equation. So you get the integral of dy over h of y equals the integral of g of x dx. And this is the approach. So the method for solving a separable differential equation is based solely on integration. You just separate the variables on opposite sides of the equation, and then you integrate. So if we call h of y the integral, the antiderivative of the left-hand side of the equation, and g of x the antiderivative of the right-hand side of the equation, then the solution we get has the form h of y equals g of x, capital H of y equals capital G of x, and we'll put a plus c at the end if we're talking about a general solution, because we have to have the constant of integration there. Now we technically get two constants of integration, one from the left-hand integration and one from the right-hand integration, but we have an arbitrary constant on the left and an arbitrary constant on the right. And arbitrary plus arbitrary equals arbitrary. You can make any constant you want out of those. So we're just going to combine that into a single constant, and we'll put it on the right-hand side of the equation with the independent variable. So let's take a look at a few examples of this technique. So suppose we want to solve the differential equation dy dx equals x squared y plus y. First thing we have to do is convince ourselves that this is a separable differential equation, and we can easily see that by factoring y out on the right-hand side of the equation. So we can rewrite the equation as dy dx equals y times the quantity x squared plus 1. So we can see that our g of x is now the function x squared plus 1, and our h of y is just the function y. So we have a separable differential equation. So the first thing we want to do then is separate the variables on opposite sides of the equation. So we move the y over to the left-hand side of the equation in the denominator. We move the dx over to the right-hand side of the equation. So we've now rewritten the differential equation in the form dy over y equals x squared plus 1 quantity times dx. So now we have the dependent variable and its differential on the left-hand side, the independent variable and its differential on the right-hand side. We have them separated. So all we have left to do now is integrate. So we have to evaluate the integral of dy over y on the left-hand side and the integral of x squared plus 1 dx on the right-hand side. And these are both easy integrals to complete. We learned about how to do both of these in Calc 2. So we get as our general solution, ln the absolute value of y equals 1/3 x cubed plus x plus c. Notice this is an implicit solution to the differential equation because we don't have the dependent variable y solved for as a function of x, but this is still a solution nonetheless. So there's our solution to this particular differential equation. A problem might also ask us to find the explicit solution to this differential equation. We have an implicit solution. In fact, some of the questions on WebAssign will ask for the answer in this format. So once we have this differential equation, how do we find the explicit solution? Well, that's easy. We just solve for y. So if we start with the differential equation in its implicit form, and we want to get the y out of the ln, the inverse of ln is exponentiation, so we would take e to both sides of the differential equation. So we obtain e to the ln absolute value of y equals e to the power 1/3 x cubed plus x plus c. Now on the left-hand side of the equation, that's going to simplify to a y. On the right-hand side, we're actually going to separate things before we simplify. Again, using the laws of exponents, right? So the e to the 1/3 x cubed plus x plus c can be separated as e to the c times e to the 1/3 x cubed plus x. And then, since c is just an arbitrary constant, e to the c is also going to be an arbitrary constant, so we can actually re-express the differential equation in the form y equals c e to the 1/3 x cubed plus x power. That c is a capital C. It's different from the lowercase c in the previous slide, but it doesn't matter. They're all arbitrary constants, so we're just kind of renaming it c. So this would be the explicit solution. In this case, we're able to solve for y. Sometimes you might get an implicit solution to a differential equation and be unable to solve for the explicit solution, and that's just the way it is. So as a second example, let's look at an initial value problem. So suppose we're asked to solve the initial value problem dy dx equals e to the power x plus y, subject to the initial condition that y of 0 equals 0. Now we only know how to solve separable differential equations, so the very first thing we need to do is to convince ourselves that this differential equation is separable, and then find the general solution to the separable differential equation using the method of this chapter, this section, and then we will plug in the initial conditions to solve for our constant of integration. So this is like an example from earlier where using the laws of exponents, we can see that the function on the right-hand side can be rewritten in the form e to the x times e to the y. So we see that the differential equation is separable. And then the next step in the process is to separate the variables and their differentials onto opposite sides of the differential equation. So it can be written in the form dy over e to the y equals e to the x dx. Then we integrate both sides of the differential equation. The integral on the right-hand side is pretty straightforward, but the integral on the left-hand side is a little bit tricky. You might be tempted to use an ln to integrate that, but that's not going to work. It's only going to work if the u in the denominator was e to the y, and you want to integrate that as an ln. That would only work if you had the derivative of the denominator, which is also e to the y, in the numerator. So it's not going to work as an ln, but what we see is that we can actually, again, use the laws of exponents, and we can rewrite the differential equation in this integral of e to the negative y dy equals integral of e to the x dx. If you go back and look, you see that the left-hand side of the equation had an e to the y in the denominator, and the laws of exponents tell us that that's the same thing as having a negative y, e to the negative y in the numerator. Now we can integrate both sides of the differential equation. The left-hand side integrates as minus e to the minus y, and if you're not sure why that is, you might want to just work out the u substitution, take a few minutes and work that out. The right-hand side just integrates as e to the x plus c. So here's our general solution to the differential. But now we want to plug in the initial conditions to figure out what value our constant c should take. So remember, our initial condition is y of 0 equals 0. And what that means is when x equals 0, y must also equal 0. So we basically want to take the differential equation. Everywhere we see an x, we plug in a 0. Everywhere we see a y, we plug in a 0. And we see what algebraic equation we get. In this case, we get minus e to the minus 0 power equals e to the 0 power plus c, which simplifies as minus 1 equals 1 plus c, because remember, e to the 0 power is 0. Now we can easily solve this equation algebraically for c, and so we get that negative 2 equals c. So that's the value of our constant of integration. C should be negative 2. Plugging that in gives us the final answer to the IVP. Minus e to the minus y power equals e to the x, and then we plug in our constant minus 2. So here's the final solution to this initial value problem. Okay, that concludes our lecture on separable differential equations. So we'll talk about this more in class.